transformer losses are an important consideration in electrical systems. To estimate these losses, we can break them down into two main components: core losses and copper losses. Total transformer losses are then the sum of these two. Core losses, often denoted as P subscript C, are calculated using this formula: P subscript C equals the kVA rating of the transformer multiplied by the core loss percentage, P subscript C percent, multiplied by the ratio of the operating load to the kVA rating. In this formula, P subscript C represents the core losses in kilowatts. The kVA rating is the transformer's nameplate rating, for example 2500 kVA. P subscript C percent is the core loss percentage. This value is typically around 0.5 to 1.5%, but it's best to obtain it from the transformer manufacturer's datasheet. Operating load is the current load on the transformer, expressed in kVA, for example 1700 kVA. Copper losses, denoted as P subscript W, are calculated using this formula: P subscript W equals the kVA rating multiplied by the copper loss percentage, P subscript W percent, multiplied by the square of the ratio of the operating load to the kVA rating, and finally multiplied by the square of the percent impedance, C, divided by 100. Here, P subscript W represents the copper losses in kilowatts. The kVA rating is the transformer's kVA rating, such as 2500 kVA. P subscript W percent is the copper loss percentage, which is typically around 1 to 2%. Again, it's best to obtain this value from the manufacturer's datasheet. Operating load is the current load on the transformer in kVA, for example 1700 kVA. C is the percent impedance of the transformer, also from the nameplate, expressed as a percentage, for example 5.62%. To determine the total transformer losses, denoted as P subscript T, we simply add the core losses and the copper losses using the formula: P subscript T equals P subscript C plus P subscript W. P subscript T represents the total transformer losses in kilowatts. Remember that the percentage values for core losses and copper losses, P subscript C percent and P subscript W percent, are crucial for accurate calculations. These values are usually provided by the transformer manufacturer or can be estimated based on industry standards for similar transformers. Firstly, gather the required data. Obtain the transformer's kVA rating and percent impedance, C, from the transformer's nameplate. Collect the core loss percentage, P subscript C percent, and copper loss percentage, P subscript W percent, from the manufacturer's datasheet. If the manufacturer's data isn't available, estimate these percentages based on industry standards for similar transformers. To determine the operating load in kVA, this can be obtained from metering data or calculated based on the current and voltage measurements on the transformer's secondary side. Secondly, calculate the core losses using the formula provided earlier. Substitute the known values for kVA rating, P subscript C percent, and operating load into the formula to find P subscript C. Thirdly, calculate the copper losses using the formula provided earlier. Substitute the known values for kVA rating, P subscript W percent, operating load, and percent impedance C into the formula to find P subscript W. Fourthly, calculate the total transformer losses. Add the core losses P subscript C and the copper losses P subscript W to obtain the total losses P subscript T. The total transformer losses, P subscript T, represent the total power lost in the transformer due to core and copper losses. These losses are dissipated as heat. Understanding these calculations allows you to monitor transformer efficiency, identify potential issues, and optimize transformer loading to minimize losses. By inputting the transformer rating of 2500 kVA and an operating load of 1700 kVA, we can estimate the transformer losses using the formulas for core losses and copper losses. Firstly, let's calculate the core losses. We'll assume a core loss percentage of 0.5%. The formula for core losses, P subscript C, is kVA rating times the core loss percentage times the ratio of the operating load to the kVA rating. Substituting the values, we get P subscript C equals 2500 kVA times 0.5, which is 0.5% expressed as a decimal, times 1700 kVA divided by 2500 kVA. Calculating this, we get P subscript C equals 2500 times 0.5 times 0.68, which equals 8.5 kilowatts. Therefore, the core losses are 8.5 kilowatts. Secondly, we'll calculate the copper losses. We'll assume a copper loss percentage of 1% and use the given impedance of 5.62%. The formula for copper losses, P subscript W, is kVA rating times the copper loss percentage times the square of the ratio of the operating load to the kVA rating times the square of the percent impedance divided by 100. Substituting the values, we get P subscript W equals 2500 kVA times 0.1, which is 1% expressed as a decimal, times the quantity 1700 kVA divided by 2500 kVA squared, times the quantity 5.62 divided by 100 squared. Calculating this, we get P subscript W equals 2500 times 0.1 times 0.68 squared, times 0.562 squared. Simplifying further, we get P subscript W equals 2500 times 0.1 times 0.4624 times 0.315844, which equals 0.365 kilowatts. Therefore, the copper losses are approximately 0.365 kilowatts. Thirdly, we'll calculate the total transformer losses. The formula for total transformer losses, P subscript T, is the sum of the core losses, P subscript C, and the copper losses, P subscript W. Substituting the values, we get P subscript T equals 8.5 kilowatts plus 0.365 kilowatts, which equals 8.865 kilowatts. Therefore, the total transformer losses are approximately 8.865 kilowatts. The core loss percentage and copper loss percentage are typically provided by the transformer manufacturer. If these values are not available, you can estimate them based on industry standards for similar transformers. These percentages can vary depending on the transformer's design and construction. Accurate values for these percentages will lead to more precise loss calculations. The load factor is defined as the average load over a period of time, divided by the peak load during that same period. It's a measure of how consistently a transformer is loaded. A higher load factor indicates a more consistent load, while a low load factor indicates a more variable load. The load factor affects transformer losses because copper losses are proportional to the square of the load. Transformers with higher load factors tend to have higher average copper losses than transformers with lower load factors, even if they have the same peak load. The formulas provided can be used to estimate transformer losses at a specific operating load. To estimate losses over a period of time, you would need to calculate the losses for each load level and then average them over the period. Alternatively, you can use the average load to estimate the average losses over the period. However, keep in mind that this approach may not be as accurate as calculating the losses for each load level. The impedance of a transformer is the opposition it presents to the flow of alternating current. It's expressed as a percentage of the transformer's kVA rating. The impedance affects transformer losses because it determines the amount of current that flows through the transformer's windings. Transformers with higher impedances tend to have lower copper losses than transformers with lower impedances for the same kVA rating and operating load. Transformer efficiency is the ratio of the output power to the input power. It's a measure of how effectively the transformer converts electrical energy from one voltage level to another. Transformer efficiency is affected by transformer losses because the losses reduce the amount of output power that the transformer can deliver. Transformers with lower losses tend to have higher efficiencies. The formula for efficiency is output power divided by input power, which can also be expressed as output power divided by the sum of the output power and the losses. When selecting a transformer, it's important to consider the transformer losses and efficiency. Transformers with lower losses and higher efficiencies will save energy and reduce operating costs. However, these transformers may also be more expensive to purchase. It's important to weigh the cost of the transformer against the energy savings to determine the most cost-effective option. In addition to the core losses and copper losses, there are other factors that could affect transformer losses, such as temperature, voltage, and frequency. Higher temperatures can increase transformer losses, while lower temperatures can decrease them. Variations in voltage and frequency can also affect transformer losses. It's important to consider these factors when estimating transformer losses and selecting a transformer for a particular application. The formulas provided are based on certain assumptions, such as the core loss percentage and copper loss percentage being constant. In reality, these percentages can vary depending on the operating conditions. It's important to keep this in mind when using these formulas to estimate transformer losses. Regular maintenance of transformers can help to minimize losses and improve efficiency. This includes cleaning the transformer windings, tightening connections, and checking the oil level. Proper maintenance can also help to prevent transformer failures, which can be costly and disruptive. The losses calculated represent the amount of power that is dissipated as heat within the transformer. This heat must be removed to prevent the transformer from overheating and failing. Transformers are typically cooled by oil or air. The cooling system must be properly designed and maintained to ensure that the transformer operates within its temperature limits. Transformer losses are an important consideration in the design and operation of electrical systems. By understanding the factors that affect transformer losses, you can select and operate transformers in a way that minimizes energy consumption and reduces operating costs. The formulas presented provide a basic framework for estimating transformer losses. For more accurate calculations, it's recommended to consult with a qualified electrical engineer and obtain detailed information from the transformer manufacturer. Consider a 2500 kVA transformer operating at a load of 1700 kVA. The transformer has a core loss percentage of 0.5%, a copper loss percentage of 1%, and an impedance of 5.62%. We can use the formulas provided to calculate the core losses, copper losses, and total transformer losses. The core losses are calculated as 2500 kVA times 0.5 times 1700 kVA divided by 2500 kVA, which equals 8.5 kilowatts. The copper losses are calculated as 2500 kVA times 0.1 times the quantity 1700 kVA divided by 2500 kVA squared times the quantity 5.62 divided by 100 squared, which equals 0.365 kilowatts. The total transformer losses are calculated as 8.5 kilowatts plus 0.365 kilowatts, which equals 8.865 kilowatts. The transformer efficiency is calculated as the output power divided by the input power. Assuming a power factor of 0.8, the output power is 1700 kVA times 0.8, which equals 1360 kilowatts. The input power is 1360 kilowatts plus 8.865 kilowatts, which equals 1368.865 kilowatts. The transformer efficiency is 1360 kilowatts divided by 1368.865 kilowatts, which equals 0.9935 or 99.35%. This means that the transformer is converting 99.35% of the electrical energy into useful output power, with the remaining 0.65% being lost as heat due to core and copper losses. The core losses are relatively constant and do not vary much with the load, while the copper losses are proportional to the square of the load. At lower loads, the core losses may be a larger proportion of the total losses, while at higher loads, the copper losses may be a larger proportion of the total losses. By analyzing the core losses and copper losses separately, you can gain a better understanding of the transformer's performance under different loading conditions. The impedance of the transformer is an important parameter that affects its performance. A higher impedance can limit the fault current, but it can also result in a larger voltage drop under load. A lower impedance can allow for a higher fault current, but it can also result in a smaller voltage drop under load. Choice of impedance depends on the specific application and the requirements of the electrical system. Transformer losses can be reduced by using better materials, improving the design, and optimizing the operating conditions. For example, using amorphous steel for the core can reduce core losses, while using larger conductors for the windings can reduce copper losses. Operating the transformer at a lower temperature can also reduce losses. Regular monitoring and maintenance of transformers can help to identify and correct problems that can lead to increased losses. This includes checking the oil level, inspecting the bushings, and testing the insulation. Proper maintenance can also extend the life of the transformer and prevent costly failures. Transformer losses are an important consideration in the design and operation of electrical systems. By understanding the factors that affect transformer losses, you can select and operate transformers in a way that minimizes energy consumption, reduces operating costs, and improves the reliability of the electrical system. These calculations provide a foundation for assessing transformer performance and making informed decisions about transformer selection, operation, and maintenance. Always refer to the manufacturer's data and consult with qualified professionals for specific applications.